In this video, I'll be teaching you how to handle electron configurations for ions, and we're also going to be building off of the electron configurations that we did using the noble gas abbreviations from the previous video. For this video, we're going to focus on the example of iron. So iron is symbol Fe, and we'll work with this, and we're also going to work with the ion of it with a 2+ charge. We'll be doing this side by side so that we can see how the two electron configurations will compare for the element as a neutral atom and the element as an ion form. So looking at the periodic table, we would see that iron has an atomic number of 26. And since that's the number of protons and the neutral atom will have an equal number of electrons, that means that we'll be looking for 26 electrons here. So to write this out using our order that we've done previously, we'll start with the 1s2, 2s2, 2p6, 3s2, 3p6. Then remember we go up to the 4s2 after that. And finally we're going to add up in the 3d sublevel and counting it out to see how many electrons we have left. We've used 20 so far, we needed 26, so we'll make this 3d6. We can also abbreviate this using the noble gas abbreviation like we've done before. So since we have 26 electrons to work with, we're going to want to choose a noble gas that has 26 or fewer electrons, which in this case will be argon. Argon will be the one that has the most without going over. Argon will abbreviate everything up until the 3p6, the first 18 electrons. And so our noble gas abbreviation would look like argon in brackets, followed by the remaining parts, which are 4s2 and 3d6. So now we're going to handle the case where we have an ion to work with instead of a neutral atom. Now, like we have mentioned before, neutral atoms have equal numbers of protons and electrons, so the atomic number will also tell us the number of electrons, but ions will not have equal numbers of protons and electrons. In this case, we're going to have a 2+ charge. So one way we could think about that is meaning that we have 2 more protons than electrons. The 26 protons will still hold because the atomic number is always the number of protons. And so if we have to have 2 more protons than electrons, that means we're going to have 24 electrons to work with here. Since we have 24 electrons, the electron configuration is going to be different because we have a different number of electrons. So let's go ahead and write this out. Again, using the order that we've dealt with before, we're going to start with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then since we only have 4 electrons left now, we're going to end with 3d4. One thing I do want to say about this is that this is the way that we will handle it for the physical science class, but in the future you may see that electron configurations will be a little bit different from what we're showing here, especially for the ions. We're going to stick with this for now, like I said, but again, there may be some differences that you will see later down the road. So now we've written out our electron configuration in the full notation, but we can also do it with that noble gas abbreviation. Again, we're going to abbreviate this portion with argon, the first 18 electrons. And then adding the rest on, we'll end up with 4s2, 3d4. The distinction I want to show here is that the 2 electron configurations that we have here, the one for the iron up on top, and I'm going to underline the noble gas abbreviation version, and then also the iron with a 2+ charge, which I'm showing at the bottom, those are 2 different electron configurations. This should make sense because iron and iron with a 2+ charge have 2 different numbers of electrons. The charge changes the number of electrons, so in this case we're going to have fewer than the number of electrons in the neutral iron. So this should be a good guide to help you through those electron configurations for the ion worksheets that we've done, showing how we handle the ion, making sure again that the electron configuration matches the number of electrons, and that will be different from what it would be for the neutral atom.